let's talk about Feynman diagrams. And we'll also talk about Feynman rules, which are essentially there to help us to write down the mathematical expressions for Feynman diagrams, or so to say, to convert Feynman diagrams into mathematics. Now, first of all, what is a Feynman diagram? Well, it is actually one of the several possible ways for a scattering process to happen. One Feynman diagram. So let's consider an example of a electron scattering process where you have two electrons. Say one electron has some momentum p and the other electron has some momentum associated to it, that is k. Now these two electrons scatter. So let's draw a Feynman diagram for this typical scattering. And so we have two electrons, they would scatter with the exchange of a virtual particle or a boson that is known as the virtual photon. And so what happens is the momentum of this electron is changed to some momentum p prime, and the momentum of this electron is changed to some momentum k prime. Now, where does the momentum go, right? That's the question. Well, due to the conservation of momentum, the momentum actually went into this momentum of the photon. So let's call it Q, which would simply then be P minus P prime for this particular electron, right? Okay, now note that with Feynman diagrams, we are not measuring what happens during the scattering, but instead we are concerned with or measuring what is happening at the external lines, which are these lines, right? So this is where we have placed our detector, which is measuring for us. Now, because of this thing, we can never be sure if this one particular diagram is actually the process that really happened. Maybe it could be that something else happened, something like which could be shown with a or depicted with a Feynman diagram that looks a bit like this, where you have these two electrons coming in and the virtual particle, well, which is a photon, it was emitted and it turned into a particle and an antiparticle pair, and then again turned into a photon, right? So let me just write this down. We had an electron with momentum p coming in, scattered with an electron with momentum k, and the virtual particle turned into a pair of particle and antiparticle, and then again annihilated each other and turned into a photon. And then what happened was you get an electron with some momentum p prime, an electron with some momentum k prime, right? So this is just one other diagram for the same process where the difference was in how the scattering happened. And so we cannot claim that yes, this one particular diagram is exactly what happened, or maybe this one particular diagram is exactly what happened. We cannot be sure. And that is simply because we never know what actually happened in between, right? By in between, I meant what happened when the scattering occurred, right? Because we don't know what happens at that time. Like I said before, we only measure at the ends or at these external lines, right? And there is what we can be sure of what happened. Now, for a particle that changes states, say from some initial state to a final state f, we have something that is actually called a scattering matrix. Now, a scattering matrix relates the two states. these two states, initial and final states, and it does so in a manner that is, you can write down initial state and final state sandwiched between this scattering amplitude, right? Now, a Feynman diagram is actually just a term in the perturbative series expansion of this particular S matrix. And that is how you can write down the mathematics of this thing, right? So in perturbation theory, we actually neglect higher order terms, right? If you have studied perturbation theory in quantum mechanics or whatever, you know that you neglect the higher order terms, and that is because they are not much of a useful contribution in what we are trying to calculate. And so we can simply neglect the higher order terms. And so we can do this exact same thing in this Feynman diagrams. We can neglect the higher order Feynman diagrams for a particular process. So by neglecting higher order Feynman diagrams, I just mean that this diagram over here is for the same process that is happening in this diagram. The only difference is it got a bit more complicated with this virtual photon turning into a pair of a particle and an antiparticle and annihilating each other again and turning back into a photon. The process is same, only the way of scattering changed. Now, this diagram, this one, is actually more complicated compared to this diagram. And so it turns out in quantum field theory, the more the complicated the diagram is, the less likely it is to contribute for a particular process. And so we can say that this diagram is a higher order diagram. And so when writing down the perturbative series, we can neglect this higher order diagram, right? And we can just consider this simple diagram for a process. Now again, remember that we are talking about scattering. So to figure out the scattering cross-section for a process, we actually happen to sum over all of the particular Feynman diagrams that we could have for one specific process, right? So what do I mean by that is simply that the scattering cross-section is directly proportional to the sum of all the diagrams that you have. I can't spell, sorry, diagrams squared, right? But again, luckily, the higher order diagrams may simply just be neglected. And that is because they will barely contribute to the total probability. So we shall simply truncate our series expansion at that particular point, right? Okay, now, of course, I know you might probably even be scratching your heads right now. What do I mean by sum over the diagrams, right? What does that mean? You cannot sum over diagrams. Well, these Feynman diagrams are actually mathematical equations. They are a bunch of mathematical equations, and they're just, well, they visually appear like these Feynman diagrams. So let's do something. Let's actually look at few of the diagrams. And so for example, let's start with a diagram or just one particular diagram for the phi-4 theory, right? Okay, so for the phi-4 theory, we could have a diagram that looks something like this, right? Okay, now one thing I would just like to mention over here, but I would elaborate it over in the continuation of this video, is that because we have 4 over here, because it's a phi-4 theory, we have, these are known as vertices, right? So we have 2 of these vertices. And for a phi-4 theory, you should have 4 lines coming out of each vertex, right? So, and you can clearly see that you have 4 lines that are coming out from each out of this vertex. Now, of course, like I said, I would elaborate at this point later in this video, because I'm pretty sure you don't understand, because these vertices and these lines, so-called, they're very important for these Feynman diagrams. And so, well, this one is for a 5-4 scalar field theory. We also have QED, which is the theory of quantum electrodynamics. And in quantum electrodynamics, you could have a diagram where you have an electron just propagating, and it could just emit a photon and absorb it back. So that's a photon represented with gamma, and this is actually called self-energy diagram, right? And we could also have one more in QED. Well, of course, we could have a lot of these Feynman diagrams for quantum electrodynamics, even for this 5-4 theory. You could have some diagram that looks something like this, where you have a vertex over here. And again, you can see that we have 4 lines coming out of this vertex. So it satisfies the 5-4 theory, right? Okay, so I was talking about QED now. And in QED, we could also have this one diagram where it looks something like this. Let me just first quickly draw it. And so this is an electron propagating something like this. And at each vertex, you have a photon. And so if you look at this diagram, you might be thinking, wait, what? Because it shows that a photon is, well, interacting with itself. And yes, theoretically, photons can interact with themselves, and that is in the very high order perturbation theory, right? In the very high order perturbation expansion of the series. Now let's talk about another one, well, very quickly, QCD, which is called quantum chromodynamics. And in quantum chromodynamics, you could have a diagram which looks, well, it looks a bit funny, but it looks something like this, where you have, and these curly lines, I don't know if I should call them curly lines, these are gluons. So we have one gluon here, another one here, and we have another one that is here, and we have quarks like this, right? So these external lines, these are quarks. Well, this one is a quark, and this one is an anti-quark. And you also have this another, sorry, I should not draw it like this. You have another gluon coming out of this, and this one is just simply for a radiative correction. Now, again, the bosons in QCD are gluons, and these external lines that you see over here, these external lines that you have, these are quarks in QCD, right? Okay. Now, again, let me just mention this, that the incoming and outgoing particles, they correspond to external lines. So we have this quark and anti-quarks, right? And well, but for different theories, right, where we have different particles, so as you can clearly see from this one, quantum electrodynamics has electrons, and photons are the bosons, and electrons are the fermions. And in QCD, quantum chromodynamics, the bosons are actually gluons, right? And these particles, the particles are quarks and anti-quarks, right? So these different theories which have different particles, they will correspond to different mathematics. But the whole idea, as you can clearly see from these diagrams of these different theories, the idea of external lines, vertices, and propagators is the same. Now, I will talk about propagators just now, actually, in fact. And so let's actually move on to, well, stripping down a Feynman diagram, right? Now, for a Feynman diagram, we have what is called external lines. So let me just write it down very quickly. we have external lines, and these lines actually are those which go from the vertex and leave the vertex, right? So something like this, where this thing is your vertex, and they go in the vertex and they leave the vertex, right? Now, this leads us to the second point, or the second item you could say in the Feynman diagram, is vertices. Now, in vertices, you have for two vertices are again where these if I go back here, if you look at this example for 5-4 theory, a very simple one, this is your vertex where these lines enter and leave the vertex, right? Okay, so well, if you have two vertices, we would have lines connecting them, right? As you can clearly see, as you can see in this example, you have two vertices and there are these three lines that are connecting them. So one is this one, the other one is this one, and we have this one. So we have three lines here for a 5-4 theory that are connecting these two vertices, and that is what leads us to our item number 3 in the Feynman diagram dish. Well, it's called a propagator. And well, the propagators are just your internal lines, as you can see over here, right? And I will talk in somewhat detail about propagator, right? Now, whatever a quantum field theory is, these three things are what makes up a Feynman diagram. So you could think of them as the ingredients to a Feynman diagram. Now, a question pops up, that is, how can we connect all of these three objects, right, together? And that actually just depends on what type of a quantum field theory you're talking about. If it's a scalar quantum field theory, or a quantum electrodynamics, or is it a quantum chromodynamics? Now, for a quantum field theory, we have what is called Feynman rules. And these Feynman rules are which allows us to translate these diagrams into mathematics. And so to look at this with more depth, we will consider an example, and let's consider an example from a very simple theory, or a very simple quantum field theory, which is a scalar field theory. And we will consider an example of phi cube like theory, right? Okay, so for a phi cube theory, one of the possible diagram would be of, well, a self-energy one, where you have, because again now it's a phi cube theory, we should have three lines attached to the vertices. So let's draw an external line like this, and then let's draw something like this, and an external line like this. Now if you look at it, these 2 points are your vertices, right? And let's just label them X and Y. And let's say you had a momentum P, particle with momentum P, and later it had momentum P prime, and these two propagators in between, let's label them as K1 and with momentum K1 and K2. Now you can see that each vertex over here has three lines connected to it, right? So these are those three lines. And for this vertex, you have this one, and this one. Right. Now, well, these external lines that you have over here, these ones, right? These external lines, they are actually given by a factor of exponential. Well, actually, let me write it down a bit like this: external lines, right? So that's the first point, and these are given by a factor of exponential negative plus p dot x, where again x is just where this you have this vertex, right? And p is the momentum associated with that particular line. So for this one, you would just have exponential negative p dot x, and for this line, you would have exponential positive p prime dot y, because the vertex over here is y. Perfect. Now moving on to the point number 3, or let's talk about the vertex. Well, vertex is where the interaction actually happens, and that depends on the coupling strength. And your coupling strength actually depends on the strength of the interaction. And for a scalar field theory, each time you see a vertex, you multiply by a factor of which is negative iota lambda, where lambda has the information of the coupling strength, right? Now, with this, then let's talk about propagators. And the propagators are actually given by solving an equation of motion for a particle. But let's give you an example. For a scalar field theory, the propagator is something like iota over k squared minus m squared plus some iota epsilon. And this iota epsilon, it actually comes from where you might have a pole at k is equal to m, or m is equal k is equal to m, right? Because then it would be not defined over that point. So to avoid that, we add iota epsilon. Now again, note that the momentum should remain conserved for this particle scattering, or any particle scattering, obviously. We impose mathematically the momentum conservation at vertices. And well, finally, we also have to integrate over the undetermined, or the undetermined momentum, right? And so that is done in a way where you have d4k over 2 pi 4. Now, if you are confused right now, we will see how can we combine all of these, right? And we will, well, we are actually looking at an example, and you will understand it more when I try to combine all of these terms, right? Okay, so, well, actually, that is what I'm going to do right at this very moment. I'm going to translate the above diagram, this one, into mathematics, right? So, well, first of all, from the conservation of momentum, we would have, if you look at this diagram, right? If you look at it, and let me get rid of these extra lines over here. Okay, now if you look at this diagram, you can see that you would have, from momentum conservation, you would have K2 is equal to K1 minus P prime, right? And well, what I can do is I can constrain K2 in terms of K1, and let me write it down. K1 minus K2 is equal to P prime. So now K1 can be anything. It can take any value. So therefore we integrate it from 0 to infinity. And let's just make things easier for us. Let's just rename K1 as simply K. Now, again, if you look at this diagram, you can see that you have these two vertices, right? And according to the rule that I just said over here, for each vertex, you add, or you multiply this factor of negative iota lambda. So if I go back here, to combine all of these things, to write down an integral for this diagram, right? It would be an integral. and that would be the mathematical expression. To write it down, we see we have two vertex, so we add negative iota lambda squared. We add it 2 times, or we multiply it by itself 2 times, and then we add this integral d4k over 2 pi to the power 4. Now you can see that you have well, if you look at this, you have this external line. Associated with it is the momentum P and the vertex X. So according to this rule, what I just do is I put exponential negative iota P dot X. Now let's go back to the diagram. Now we have these two internal lines, or these two propagators. So to write down the expression, considering this is what we have for propagators in a scalar field theory, what I would have is, I would have iota over, well, for k1, let's write for this one, this internal line, k1, and I said it's just equal to k. So I would just have k squared minus m squared plus iota epsilon, right? And let's just make this a bit smaller. And we also have another line over here, another internal line or another propagator, but it is for k2. So writing down that in terms of k1 or just k, it would be k minus p, right? Okay, so you can see that from this thing. So it would be iota over k minus p squared minus m squared plus iota epsilon, right? Now we have accounted for these two internal lines in this diagram. We are just left with this external line, and well, for this external line you can see external lines rule over here, and that is, it would be exponential positive p prime dot y, because we have vertex y associated to this. So let's just put that in, exponential iota p prime dot y. And boom, there is your mathematical expression for this particular diagram. And I know I made the diagram a bit messy, but I hope you can understand it. Let's just get rid of these extra lines. Okay, so this is your diagram, and this is the mathematical expression for it. Or this is actually the integral that you would be computing to find the self energy in phi cube theory, right? Because this diagram is what is called a self energy diagram, right? Okay, so well, this was the whole point of the video, to tell you or to show you what a Feynman diagram is and how can you write down the Feynman rules for a particular Feynman diagram. But of course, I am definitely not going to solve this integral, and that is because it is a very extremely, well, actually complicated integral. And well, that is because if I look at this expression and I consider the powers of k in this expression, I have 4 powers of k that we are multiplying over here, right? And if I look at this, I have d4k from here. I can write d4k as k cube dk, and this integral would become something like, I would have k4 over here. And now for large values of k, I would have something like something exactly like dk over k. And this integral we know is ln logarithm or natural log of absolute k. But this thing is actually the logarithmic divergence. That is, it is an infinite values, And so what you would get from here is actually a big fat infinity. Now, to get rid of this infinity, you have some procedures, and they are called regularization of your integral, or the dimensional regularization, and renormalization. So, of course, I am definitely not going to do that in this video. The whole point of this video was to get you, well, at least acquainted with what Feynman diagrams are.